Good evening. This work is based on simple reactive neural networks for behavior-based reinforcement learning. This work was carried out at the Computer Vision and Autonomous Systems Group at the University of Glasgow. And we'd like to acknowledge ICRA Pune and Erasmus Plus team for the International Exchange Program support and NVIDIA for all the resources that are being used in this work. So in this work, we present a behavior-based reinforcement learning approach in which simple, fully connected feed-forward neural networks are trained as reactive behaviors. Our working assumption here is that a pick-and-place task can be simplified by using human knowledge, and it can be decomposed into simple reactive behaviors such as approach, grasp, and retract. Then once these low-level behaviors are trained, a higher level reinforcement learning policy can be learned to determine the activation and inhibition of these reactive behaviors in a particular temporal sequence to accomplish the task. Our method is inspired from Rodney Brook's subsumption architecture, in which complex behaviors subsume a set of simple behaviors, and the task is accomplished by activating the appropriate behaviors given a state input. Our results suggest a drastic reduction in training time compared to existing reinforcement learning approaches. So let's look at some of the background study and related works in the field. Recently, hierarchical reinforcement learning has shown success in operating at different levels of temporal abstraction by using multiple layers of policies that are trained to perform decision making. The lowest level policy of the hierarchy applies actions to the environment, whereas the higher level policies are trained over a longer time scale. However, most hierarchical approaches are trained end-to-end, and they learn multiple policies in parallel. What this means is that hierarchical approaches autonomously decide how to segment the main task into subtasks. The segmentation is task-specific, and the decomposed subtask, once trained, can rarely generalize to different high-level tasks. In our approach, we attempt to learn behaviors incrementally. Our work is very closely related to France et al. 2017, in which shared policy primitives are trained end-to-end over a distribution of tasks, and these sub-policies are switched and are activated by a master policy and a master controller. Now, on the contrary, instead of an end-to-end strategy, humans tend to learn simple behaviors first in order to compose complex behaviors. For example, while learning tennis, we start by learning basic behaviors such as bouncing the ball, hitting the ball, to name a few, whereas an end-to-end learning approach would attempt to optimize all possible behaviors all at once. Now, current model-free reinforcement learning algorithms, they require millions of trial and error attempts to learn simple tasks on simulations and games, whereas humans learn these behaviors in 50 to 100 attempts. Reinforcement learning agents start solving each problem without any prior knowledge about the world, leading to data inefficiency. Now, in our work, we use a simulated environment based on OpenAI fetch pick and place environment. This environment is used as a benchmark for testing continuous control algorithms for tasks such as robotic manipulation. The goal in this environment is to grasp a randomly positioned block and lift it to a target position. And the environment provides kinematic values of position, velocity, and orientation of the block, end effector, and the gripper. In most studies related to RL, the gripper orientation is fixed, and also the block orientation is fixed in order to reduce the task complexity. In our implementation, we go beyond the standard setting and include additional degrees of freedom of gripper rotation to grasp the block at different orientation. Here, as I mentioned before, the action space is continuous movement of XY of the end effector in the XYZ Cartesian space. And each episode here is 50 time steps. So let's look at the methods. Firstly, the whole task is manually decomposed into 3 behaviors: approach, grasp, and retract. We train a neural network to learn low-level behaviors using demonstrations. For that, we specifically used behavior cloning to mimic the demonstrations. We consider 5 different strategies here. First one is sequential. In this, the approach behavior is trained using hand-engineered solutions for grasp and retract. Now, once the success rate reaches higher, we stop the training and we train the grasp behavior using the output from the pre-trained approach behavior, while hand-wiring the solutions for the retract behavior. And similar steps are followed to train the retract module. Finally, these behaviors are put together and they are manually sequenced. Second is the sequential plus freezing strategy. In this, similar steps are followed as done in the sequential strategy, except the weights for the feature extraction layer are frozen after initial training of the approach module. We argue that once the robot knows how to perceive the state inputs, there is no further advantage to learn the feature extraction layer again. A third is the separate strategy. In this strategy, the approach module is trained first using hand engineered solutions for grasp and retract. Once the success rate reaches higher, the grasp module is trained with hand engineered solutions for approach and retract. And similar steps are followed to train retract module. Now, unlike the sequential strategy, here all modules are trained independently. And finally, they are put together and manually sequenced. Fourth is the separate plus freezing. In this case, similar steps are followed as in the separate strategy, except the weights for the feature extraction there are frozen after training the approach behavior. And finally, the last strategy is an end-to-end control strategy in which behaviors are not decomposed and the complete task is learned using behavior cloning from the start. Here are our results. The first peak, denoted by A, represents the training completion for the approach module. B represents the training completion for the grasp module, and C represents the training completion for the retract behavior. Note that after each behavior is trained, the success rate drops to 0 since learning a new behavior starts from scratch. And here step D denotes the manual combination of A, B, and C to complete the whole task. What we observe here is that it takes similar number of training steps, training episodes for the end-to-end and all the sequential strategies. Separate without any freezing shows a slight increase in the success rate, but this trend is close to an end-to-end approach. However, separate plus freezing shows a drastic increase in success rate. In this case, the robot learns each skill separately with freezing layers after initial training. And our behavior-based approach reaches 100% success rate in 6,000 episodes of training. This result suggests that learning can be more effective if each skill is learned in isolation and then combined in order to learn a higher level task of pick and place. Secondly, once the feature extraction layer network learns the latent feature space, freezing the knowledge shows more learning potential for subsequent behaviors. The best performing strategy is separate plus freezing, and we therefore use this strategy to develop a higher level reinforcement learning policy, also called the choreographer, that learns to sequence these behaviors. The choreographer uses features from the feature extractor and selects the behavior based on reward feedbacks. We consider two different reward settings here, sparse and dense. In sparse reward situation, the robot receives rewards after it completes the whole task and picks the block to a target position. In dense reward scenario, the robot receives a reward after each successful completion of a behavior. This represents a simple reinforcement learning setting where an agent has to decide the actions to maximize the total cumulative reward. We start training the high-level choreographer after 6,000 episodes. And by further inspecting the figure, we can observe that separate plus freezing combined with high-level choreographer achieves high success rate in approximately 8,000 episodes, effectively using 2,000 episodes for training the high-level reinforcement learning choreographer. This result suggests a drastic reduction in the number of training episodes required by an end-to-end approach, and the existing state-of-the-art reinforcement learning approaches such as deep deterministic policy gradient and hindsight experience replay that takes 95,000 episodes to learn the same grasping task. To conclude, our results suggest that training can be more effective if each module is learned separately with other modules already trained, and also the freezing of feature extraction layer after initial training and using this layer for training other modules shows a considerable reduction in training time. It aligns with a paradigm of bottom-up learning approach where complex behaviors could arise by generating and combining simple ones. We train all the simple behaviors independently and then combine them to complete the task. Our results also suggest that tapping into human knowledge to decompose simple behaviors and separately learning these simple behaviors shows a drastic reduction in training time. Finally, our future works would concern deploying these algorithms in a physical real robotic system in which knowledge acquired by conducting a pick and place task can be generalized to other unseen objects. Thank you.